残酷な天使のように少年よ神話になれ青い風が今胸のドアを叩いても私だけをただ見つめて微笑んでるあなたそっとくれるもの求めることに夢中で運命さえまだ知らない痛いけな瞳だけどいつか気づくでしょうその背中には遥か未来目指すための羽があること残酷な天使の手で窓辺からやがて飛び立つほとばしる熱いパトスで思い出を裏切るならこの空を抱いて輝く少年よ神話になれ
Okay, what's up guys? We're back with section 5.3, the fundamental theorem of calculus. Here's where it gets real. Here's where we see just how real it really gets. So, basically the idea of it is that when we were evaluating definite integrals using limits of Riemann sums, which we didn't even actually bother doing because it was so complicated and difficult, we talked about this in the previous section, but usually this whole process that we described is not really possible or practical in any reasonable sense. Fortunately, however, there is a powerful and practical method for evaluating definite integrals, which is exactly what we're going to develop in this section. Along the way, we're going to find out a lot about the relationship between differentiation and integration. And this is expressed by what is the most classic, the most powerful, the most important, at least to a lot of people, result in all of calculus, aptly named the fundamental theorem of calculus. So let's go. Let's get some groundwork and let's get there. Okay, so the first thing we're going to need in our journey towards the fundamental theorem of calculus is a definition. We're going to need the idea of an area function. So start out with f, a continuous function, for all values of t greater than or equal to a, where a is some number. So it's continuous to the right of some point. The area function for f with the left endpoint a is just the function a of x is the definite integral from a to x of f of t dt. Okay. And here we're assuming that x is greater than or equal to a. So a of x is the area function. And this bad boy gives the net area of the region bounded by the graph of f and the t-axis on the interval from a to x. So if we want to draw a picture of this and get an idea of what's going on, let's do it. Let's get a quick sense of what's happening. So if we just sketch out some function, here we go. Let's pick a point. Let's call it, I don't know, A. Fair enough. If I take A, I could trace on up. And the idea of it is that if this guy here is y equals f of, I'll call it x, f of x. Why not? It's all good. Or f of t, whatever you want to call it. Let's even keep it consistent and call it f of t right here, so that this is the t-axis and this is the y-axis. Then what's really going on is that if I pick an x, let's pick an x, say right here, and trace on down, then if I look at the area under this curve, the net area, so adding this area and subtracting off this area down here, then what I'll get is what the area function tells me. That is oops, get the opacity back up. There we go. This guy and this guy, the net area is a of x, which once again is just given by the definite integral from a to x of f of t dt. Cool. So that's what this is telling us. It's telling us what the net area is between some fixed point that we've already chosen, a, and a point that we put in, x, and we're getting out the net area, the area above the x-axis and below the graph minus the area below the x-axis and above the graph. All right, cool. So area functions. Basically think of the x as a slider. As you move it over, you get different net areas. Fair enough, okay. So one thing to notice here that I think might throw some people off is that x is the upper limit of the integral. It's the upper limit of the integral. It pops up right up here. Okay. And the independent variable in the area function is the same. It's x. So x is both the upper limit and the independent variable. As you change x, so does the net area under the curve change. But because the symbol x is already in use as the independent variable for a, it's the thing we're plugging numbers in for, we have to choose a different symbol for the variable of integration. That is, we're picking t here. We're doing f of t dt in this integral. We can use any symbol except x, and this is just because it's a dummy variable. It's just like when we were dealing with summation notation. It's just the same thing as when we were dealing with or sigma notation, whatever you want to call it. It's the exact same thing. It's internal to the definition here, and it's not like we're plugging something in for t. It gets used up when you evaluate the function, but to write the function down, you need that variable. So you could use any symbol you wanted. This is exactly the same as the definite integral from a to x of f of a symbol looks like a star, d a star, or the definite integral from a to x of f of smiley face, d smiley face. Okay, same thing. It doesn't matter. It's just a placeholder. It's just a symbol so we can represent everything nicely and cleanly. It's not like we're plugging something in for it. It's just internal to the definition. We need it to write the definition, but we could choose any variable we want other than x because x is already the independent variable of our function. I know that seems kind of convoluted, but basically just think of it like you're throwing some other letter there because you already used x and you can't use it again. Okay, fair enough. So there's a little bit more. Let's get into it. Okay guys, so the fundamental theorem of calculus is so important to us that it's going to get two parts. And really this just makes it easier to explain. They're ultimately equivalent, but it'll be a lot more sensible if we present them separately as if they are different parts. So, fundamental theorem of calculus, part 1. Once again, we start with a function f, which is continuous, and now we're doing it on a closed interval. So f is continuous on the closed interval from a to b, and we take the area function, just like before. A of x is the definite integral from a to x of f of t dt, and it's defined for, well, values that make sense here with the continuity of f. It's defined between a and b. Okay, cool. What the fundamental theorem of calculus part 1 is going to tell us is that this guy is continuous on the closed interval from a to b. That's fair enough. You started out with a continuous function. I don't think it's that weird to expect that the area would vary continuously as well. But the weird part is that it's differentiable on the closed interval from a to b. So notice, we started out with just a continuous function, an arbitrary continuous function, any old continuous function you want, and when you form the area function for this continuous function, then you get back a continuous, and not just continuous, in fact, a differentiable function. Whoa, that's actually kind of a lot. We take a continuous function and we get a differentiable function. It gets way weirder though. It gets way more cool. The neat part is that the area function satisfies a prime of x is equal to f of x. That is the derivative with respect to x of the definite integral from a to x of f of t dt, it's just f of x. The derivative of an area function is the original function. That's pretty cool. It's an antiderivative of f on the closed interval from a to b. Wild. If you want to say it a different way, just to really see how crazy this is, notice, like I keep stressing, f is continuous on a closed interval. That's all we assumed. So this really covers every single continuous function on a closed interval. What we found out is that that function is the derivative of an area function. If you reverse this, what this says is that every continuous function on a closed interval is the derivative of an area function. Continuous functions are the rates of change of areas. What? It seems crazy. It seems like there should be other ways to be continuous other than being the rate of change of an area, but this tells you that there isn't. There is no other way to be continuous other than by being the rate of change of an area. That's bizarro. Basically, it says if you're not continuous, well, then you certainly can't be the rate of change of an area of a continuous function. Huh, weird. So it's kind of mutually exclusive categories. Pretty cool. Okay, so let's really dig into this a little bit more and get to part 2. So like we just saw, a of x, the area function, is an antiderivative of f on the closed interval from a to b. It turns out that it's just a short step away, or we just have to take one short step to get to a very powerful method for evaluating definite integrals. We won't have to do any of these limits of Riemann sums, none of that fancy stuff. We can do a very, very powerful trick right here. So, basically, all of this just relies on one simple fact. So, remember from the earlier stuff we were doing, recall any two, all of them, any two antiderivatives of f differ by, at most, a constant. So, if big F is any other antiderivative of little f on the closed interval from a to b, then big F is just the area function plus a constant for all the x's between a and b. Okay, so if a is an antiderivative, then all of the antiderivatives are just of the form a of x plus c. So, since a of x, just really quickly to recall, a of x is equal to the definite integral from a to x of f of t dt, then a of a is equal to 0. That is, this part right here, this is just saying that the definite integral from a to a of f of t dt is 0. That is, we're taking the area under a curve, but we're doing it over an interval with 0 width. So we get out 0 area. Yeah, fair enough. Okay, now here's the trick. Here's the part that's cool. Here's the part that's surprisingly simple for how powerful of a result it gives us. Just evaluate any antiderivative of f at the endpoints and take the difference. So f of b minus f of a, well, using the fact that every antiderivative is of the form a of x plus c, what we get is a of b plus c minus the quantity a of little a plus c. And just running through a of little a, well, that's 0, and I have a plus c, and I have a minus plus c, so I have c minus c. Those guys cancel each other out, and hey, what do you know, I'm just left over with a of b. But hey, a of b? Well, look at the definition of a down here. A of b is just the integral from a to b of f of x dx. Oh, wow. Okay, this is a definite integral. I have figured out a formula to tell me the value of a definite integral. This is part 2 of the fundamental theorem of calculus, so let's talk about it. Okay, so the little trick we just used basically gives us the second part of the fundamental theorem of calculus. So part 2 of the fundamental theorem of calculus, basically what we just saw. If we've got a function f that's continuous on a closed interval from a to b, And big F is any, literally any one you want, any antiderivative of little f on the closed interval from a to b. Then, and this is the real meat of it, the definite integral from a to b of little f of x dx is f of b minus f of a, where we're taking big F in the second part of that, the part to the right of the equal sign. All right, so it's often customary and convenient to denote the difference f of b minus f of a by, and this is just some notation, this is not a new concept, it's just some notation, it's just shorthand, it's just a nickname. But we denote this by f of x bar subscript a superscript b. So this is read as f of x evaluated from a to b. So the gist is that, like we've seen before, if I write, say, f of x, then the bar, and then a, this is just saying f of a, right? Evaluate f at a. This is a minor extension. Basically, if I put the b up here, then what I'm instead going to get is just f of b minus f of a. I'm taking the difference from the top to the bottom and putting them in my functions. So f of b minus f of a, the difference of the function evaluated at the top part minus the function evaluated at the bottom part. Easy enough. Okay, just shorthand to make it a little bit easier, because when you use this, it just says that the definite integral from a to b of little f of x dx is f of x evaluated from a to b. All right, cool. This notation right here will make it a little bit easier to say some stuff later on. It'll save you some time writing things out. It's just a little bit of extra shorthand because, you know, mathematicians, a little bit lazy sometimes. Cool. So let's talk about this some more. Let's do an example. Let's really dig into it now that we've got both parts of the fundamental theorem down. So now that we've got them here, now that we've got both parts of the fundamental theorem of calculus stated and out in the open, it's worth pausing to note that this really tells us something about the relationship between differentiation and integration. Like I've been saying the whole way through, like I said right at the start, what this highlights is that differentiation and integration basically are the same thing but in opposite directions. So the gist of it is that part 1 of the fundamental theorem says that the derivative of the area function is the original function. That is, d dx of the definite integral from a to x of f of t dt is just f of x. That is, the derivative of the integral of f is f itself. I'm going to even box that because that is such an important point right here. This is one of the main little pieces. The derivative of an integral is the function. Okay, so since f is an antiderivative of f prime, that is, f is certainly something that derives to f prime, any function derives to its own derivative, that's, you know, tautologically true. It's basically a boring statement, right? Part 2 of the fundamental theorem of calculus says that the definite integral from a to b of f prime of x dx is equal to f of b minus f of a. So you take the definite integral of a derivative and you get back the difference of the function itself at 2 points. This basically tells you that when you integrate a derivative, you undo the derivative. That's pretty cool. That's pretty useful. So we've got 2 pieces. Basically what we've got is that the derivative of an integral of a function is the function itself, and the integral of the derivative of a function is given by the function evaluated at 2 points. So it's not exactly the case that the derivative of an integral is a function and the integral of a derivative is also the function. It's that the derivative of the integral of f is the function, while the integral of the derivative gives you information about the values of the function at a point. Okay, what ultimately, up to these kinds of minor distinctions, this tells us is that integrals undo derivatives. And looking at this first result right here, derivatives undo integrals a little bit. Kind of cool. Okay. All right, we're cooking with fire now. We got the fundamental theorem of calculus down, both parts of it. We've got it down in all its forms. We understand that derivatives and integrals are closely related. And now, let's do an example. Let's put it all to action. Let's see really what's going on now that we've talked about the general idea. So, example 4, let's evaluate the definite integral given by the definite integral from 0 to 10 of 60x minus 6x squared dx by using the fundamental theorem of calculus. Let's evaluate this guy making use of what we just learned. So, first thing we're going to want to keep track of is that we need an antiderivative. So if we use the antiderivative rules from section 4.9, some stuff we did really recently, an antiderivative of 60x minus 6x squared is 30x squared minus 2x to the third. That is, all we're doing is we're taking the indefinite integral of 60x minus 6x squared dx. We're using the power rule, the backwards version of the power rule we used for derivatives, and we're getting 60 over 2x to the 2 minus 6 over 3 x to the 3 plus a constant. Doing a little simplification, this just turns into 30x squared minus 2x to the third plus the constant. And since we can choose any antiderivative we want, we can choose any one we feel like, let's just make our lives easy and take that constant to be 0. Get rid of it. No constant left. We're done. We'll just kill it. And what do we got? We got an antiderivative, 30x squared minus 2x to the third. This is generally a good tip. Don't choose any value other than 0 for your constant unless you have a particularly good reason to. It'll just make you waste time. So, now that we've got an antiderivative, using the fundamental theorem of calculus, the value of the definite integral of 60x minus 6x squared dx from 0 to 10 is just given by 30x squared minus 2x to the third, an antiderivative, evaluated from 0 to 10. All we do here, all this notation means, is that we plug in the top number in for x, we put a minus sign, and then we plug in the bottom number for x, and then we just plug and chug from that. We're good to go. We did it. So 30 times 10 squared, that's 30 times 100, that's 3,000. Minus 2 times 10 to the third, that's minus 2 times 1,000, that's minus 2,000. The second part of it, this whole thing over here, it just stuff times 0. So it's 0. We get 0 right there. So 3,000 minus 2,000, 1,000. Final answer. That's what the value of this definite integral is. That is the area under the curve 60x squared minus, or 60x minus 6x squared is the net area under the curve and above the x-axis minus, the area below the x-axis and above the curve, the net area for this function between 0 and 10. It's 1,000. Cool. We didn't have to mess around with any Riemann sums. We didn't take any limits of Riemann sums. We did no approximation. All we really did is we took something that we already knew how to do. We took some info about indefinite integrals, and we calculated one of those. Then, using the fundamental theorem of calculus, and now you can see why it's so dang useful, we were able to evaluate something that otherwise would have been ridiculously complicated, would have taken a super long time to deal with, and generally is just annoying. We evaluated it in like 45 seconds. It was like nothing. And this is generally the theme of why people care about the fundamental theorem of calculus. You want to evaluate a definite integral, do an indefinite integral, and then, like we saw right here, all you got to do is plug in two numbers. So definite integrals, no harder than indefinite integrals, because all you got to do for a definite integral is take an indefinite integral and then plug in two numbers. That's pretty dang nice. Neat. We'll do a bunch more examples next time, but let's quit for today and give it some time to sink in. Cool.
are we still here? Just to suffer? Every night, I can feel my leg, and my arm, even my fingers. The body I've lost.